Hello, friends. MoNaCo here. Our third lecture in nuclear chemistry. We're going to focus mostly on transmutation in this particular lecture. And I want you to be able to distinguish between nuclear fission and nuclear fusion. So it's not just two letters different. There is something bigger to that. I want you to describe the relative amount of energy that's produced in both of them. So which one produces more energy, nuclear fission or nuclear fusion? We're going to look at some advantages and disadvantages of each type of transmutation. And I want to relate this back to that famous E equals MC equation, E equals MC squared equation, pardon me, that Albert Einstein postulated in 1905. Oh, wow, 110 years ago now that he was working on this type of stuff in his mind. So, how are nuclear fission and fusion similar? How are they different? Well, I think of them as opposites. Nuclear fission and fusion are both transmutation reactions that produce energy from nuclear reactions. Anytime a radioactive particle falls apart, there is a very, 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 very small percentage of its mass that is converted into energy. This connection is through that E equals MC squared equation, which is basically the amount of energy an object contains within it is equal to the mass of that object times the speed of light squared. Now, the speed of light is very large, so when you square it gets even bigger. And so even if you take something like a couple protons or a couple neutrons and convert them completely into energy, it's a lot of energy when that happens. Okay, so whenever we see these in paper, usually there's like some blasts, kapow, that's denoting the amount of energy that is being produced, which is a lot for reactions. So artificial transmutation, I've been saying this all along, transmutation is when one atom turns into another. Artificial is what happens when we bombard the nucleus of an element with a high energy particle. So it's like we're like shooting like pew pew particles get shot at, a bigger nucleus, And as a result, you get sometimes, you get things to fall apart. And you get maybe like, a smaller nucleus or two and, some other particles and stuff that come out of it. And every time this happens, you get energy. Lots of it. Lots and lots and lots of it. So nuclear fission. This was discovered after Albert Einstein postulated that it was possible in 1905. It's when a larger atom, like the kind of one I drew, splits apart into smaller particles. This can be forced in nuclear reactors and nuclear bombs to produce energy. Here's an example of it that is actually happening in, oops, I hit the wrong button, happening in nuclear reactors and nuclear bombs. Uranium captures a neutron, it's hit with a neutron, and it breaks apart into like barium and krypton and more neutrons. This is one possible pair of fission fragments. One of the things about these is that they're not always guaranteed as to what's going to come out of it. But what does definitely come out is we get 3 more neutrons, which can go out and hit other uraniums and cause a chain reactions. So chain reactions can result. And basically, a nuclear reactor controls that chain reaction and uses it to make heat and electricity. Now, a nuclear bomb lets that chain reaction go out of control and produces, heat and energy and an explosion that is very devastating. A nuclear reactor that's on runaway, it's on a meltdown, is also a chain reaction that's out of control. Let's see if our video here shows. We've got a uranium nucleus. We're going to hit it with a slow-moving neutron. Pow! It makes it unstable as a result, and then boom, it splits apart into something else, barium, krypton, and other neutrons, which are usually the products. Like I said, that's not always a guarantee. Some of these things, if they're left to go out of control, can make some very messy radioisotopes, which cause serious damage and cancers and all that kind of stuff. So nuclear reactors gone out of control, or A-bombs gone out of control, can cause some serious health problems, as we know. Energy is also produced in nuclear reactions because a small amount of that mass is turned into energy. One disadvantage of fission, thermal pollution is a byproduct. Thermal pollution, basically you're producing so much heat in this reaction that you can't use it all. So you use it to cool down, you use it to boil the water, you pump the water back into the lakes, oceans, streams, it kills fish. Not such a great thing, but we do need electricity, and this produces electricity without carbon dioxide, which is a global warming gas. Now, the opposite of fission is fusion, and this is happening in our star, which we call the sun. The sun is a giant ball of fire in the sky because of nuclear fusion. And lighter nuclei are combined to produce heavier nuclei. So the light stuff in the universe combined under gravity or incredibly intense pressure to produce heavier nucleus or nuclei. So in our fusion reactors here on Earth, we need this stuff called tritium, which is an isotope of hydrogen, and deuterium, another isotope of hydrogen, to make helium, a neutron, and a buttload of energy. Now, the problem is that tritium and deuterium are hard to come by, rare, and they themselves aren't very stable. So to get a fusion reaction to happen here on Earth is very challenging. The National Ignition Facility in, I forget exactly where it is, they're doing research based on this stuff to try and get a fusion reaction to go on our planet to harness its energy. The energy that's being produced by the sun is constant and ongoing, and it's being produced by gravity. Essentially, the sun's so heavy that at its core, hydrogen is being fused to other hydrogen to make helium and a ton of energy. So that's why our sun glows the way it is, and it's so big. It keeps itself going. Here's some other examples of fusion. Notice the masses are always equal. 1 plus 1 equals 2 plus 0. So the mass is equal, and the atomic numbers are always going to be equal. So we're always conserving mass and charge. Just because we're building things up doesn't mean we get to break the rules. Now, in this example, we've got many examples. We've got hydrogen plus a neutron becoming a hydrogen isotope. We got hydrogen 1 plus another hydrogen 1 becoming a helium 2. Two hydrogen 2s, deuteriums, becoming a helium 3 and a neutron. So all of these examples we have here are showing fusion. Small particles become larger particles, subatomic particles. Now, so there's some advantages and disadvantages to all this. Advantage to nuclear fission, big things breaking apart, is that you can produce heat and electricity without producing carbon dioxide. Disadvantage to nuclear fission is that the radioisotopes that are produced and used are extremely radioactive. They produce a lot of gamma radiation, and they're long-lived, meaning if I have spent nuclear fuel rods from my radioactive reactor, they're going to be radioactive enough to kill people for the next 100,000 years, if not longer. So that's a big disadvantage for fission. Now, fusion has some advantages. Lots of energy is given off, and there's not really any radioactive waste produced. Sun uses a fusion reaction to create energy. So that's great. Disadvantages, however, we need to overcome the need for extreme heat to develop materials strong enough to withstand heat and difficult to contain the nuclei in a small enough area to control the reaction. So we want to control a fusion reaction. We just don't have the materials science on our planet to actually do it. Okay? I mean, think about it. The sun is a gigantic ball of fire that does this whole fusion reaction based on gravity. We can't produce those conditions here on Earth yet in a way that makes this reaction controllable and a chain reaction. We could get it going for a few billionths of a second or so, but that's just impractical if you're trying to produce enough energy for an entire city or country or globe to work on. Now, energy is produced as a product in both fusion and fission reactions. But where does that energy come from? The total mass is less than the original mass of the reactions, which leads to. So we're talking about we're missing a few protons. You know, a few subatomics go missing. This is not included in our balanced equations because we don't take account that energy had some mass or some mass was converted into energy. We call this a mass defect. So the small amount of mass involved in those nuclear reaction is lost and converted into energy. So his famous formula, Einstein there, says energy equals the mass times the speed of light squared. So even if you had 1 AMU, so the energy 1.0 AMU times, I think it's 3.8 times 10 to the 3.0 times 10 to the 8th. 3.0 times 10 to the 8th squared. If I did this mathematics on my calculator, I hope it doesn't go into a stack overflow and die. 3.0 raised to the power of 8 squared. This is going to equal some astronomically huge number. And this is one proton. 4, 3, 0, 4, 6, 7, 2, 1. That's one like microjoules or something like that. That's one AMU got turned into that many units of energy. Now imagine if you can convert a kilogram or 2 kilograms or 120 pounds. A ton of energy is going to be produced. So if you can convert a few kilograms of radioactive material into energy, my goodness, what a massive explosion would ensue. I'm not exactly sure of the number, but I don't think a few grams, a couple grams of mass was converted into pure energy during the bombing of Hiroshima and Nagasaki, and it produced a massive amount of devastation. So at this point, I want you to be able to distinguish between fusion and fission. Describe how much energy is produced. Per unit volume, fusion would produce more energy, but fission is more common on our planet. Advantages and disadvantages of each type, and how E equals mc squared relates to the mass defect and the energy produced in a nuclear reaction. Practice Pack 4 through 8's got some more balancing and transmutations. I got a prep and a quiz for you on this material, and only one more lecture for the year. Thanks for watching. Talk to you later.